what is Lagrange multiplier, right? Do you ever wonder what U sub looks like in multivariable, multiple integral? Oh, you never wondered, right? Well, we're gonna have to do it, so let's start wondering, right? Because we haven't done U sub. I mean, there's an integration by part in multiple integrals too, but that's like kind of beyond the scope of this course, but it shows up in college. But like U sub itself. So let's review U sub. What is a U sub, right? U sub is really a change of variable. Okay, so I'm going to take this as an example. Say we have this integral, e to the sine x cosine x dx. I mean, we can do this in our head, but let's not do it in our head for the review purposes, okay? When we say u is equal to sine x here, right, we are changing this variable from x to u. So this is really change of variable. You get it? I'm going to write this down. This is change of variable, because that's the topic of Lagrange multiplier. Okay, then we have to figure out the u. Of course, that's cosine x dx, right? Right. Okay. And then let's say this is not so smart class. And then, yeah, that's cosine x, so that's u du. I used to teach you like that, but I have taught the dumb class as well, and they don't get it. So the way they have to understand is dx is equal to du over cosine x, and then you plug it in right there. So this thing becomes e to the u, and there's a cosine x, and this is the u over cosine x, and cosine x cancels. Is how they do it. I know it's sad now, isn't it? But yeah, that's how most teachers teach it. You kind of get the idea, right? So instead of writing it like this, I'm going to modify in order to get to today's lesson, which is Lagrange multiplier, right? What is dx over du? That is 1 over cosine x, isn't it? Say yes. So let's go back here. Erase. The computer seems to be stuck. Erase. Let's go back here. So we are multiplying dx over du here, which is 1 over cosine x. You know what I'm saying? Say yes. And then we can put du. Do you understand what's going on? This is just 1 over x to cancel that thing. So far, so good. Let's generalize this idea. So let's say we have some kind of f of x dx. Okay, now we want to do the change of variable, so we say u is some function of x. Good. What that means is now we are putting this thing as a f of, and this is x, but x itself is a function of u. So far, so good. Okay, now then what the heck do we put here? You get it? Before we say du, this is not just does not happen because of that dx du relationship. You know what I'm saying? So what we put here is dx over du is what goes here. This is the key, right? That's exactly the same thing here. So if you want to go back, oh, these two cancel, dx, and that's x. You know what I'm saying? But we want to be able to integrate with respect to u, right? Another way of saying this is x is equal to inverse function of u. You know what I'm saying? Okay, so far so good. Oh, yeah, this is x, that's this thingy that goes in here, okay? So this is known as Lagrange multiplier, dx over du. in order to make this relationship, right? The one that ties dx to du and then make us to do the substitution, which we called u sub last year, right? Which is really change a variable. You with me now? Now we'll do it in double integral. Okay, say double integral. Say we have some kind of region. Do they usually call it D in this book, right? I used to call it R, but hey, whatever. X, Y, and then dx, dy, dx, whatever. Right? We want to convert this. Let's just convert it. Oh, this is concrete example. Let's color code everything. I'm gonna change that to blue. Okay. Suppose we want to change that to, because this we are also used to it, to polar coordinate. Good. And then what we need here, if you remember, the dA in polar was r dr d theta, right? And then I want you to concentrate on that r, because I kind of justify it geometrically, that r, right? Where does that r come from? I like to formalize that and then change it, apply it to any double variable or triple variable situation. So this is a generalization, okay? Okay, first of all, polar coordinate, of course, looks like this. Say we have this, and I'm gonna throw the picture. Does it look like center? Yep. Okay. This is polar coordinate with x and y thingy, right? But has it ever occurred to you we can actually have r theta coordinate? What does r theta coordinate look like? Well, let's say this side is r, this side is theta, or we can switch it, whatever, right? Okay, so far so good. So this circle, let's say if this is a radius of r, capital R, what's the area of this thingy? Pi r squared, of course, right? What does that look like here is the question. And then answer is, it'll look like a square. I mean, some kind of rectangle. You know what I'm saying? Because r increases from 0 to r and theta increases from 0 to 2 pi. Are we good? And then, of course, we're missing r, right? That r. Because if you calculate this area, it does not become this. You know what I'm saying? So if this is capital R here, that length, I'm going to put it like this. And this is 2 pi. That really doesn't work. You know what I'm saying? Okay, so, and this thing is going like around 2 pi. But you see coordinate transformation idea, right? Instead of xy, r theta is better. Okay, now I'm going to zoom in and throw this tiny little thingy. So here, say there's a tiny little thingy right here. This is what we call dA, right? And we used to call this thingy r dr d theta, right? We just got it out of geometry. Good. And then here, of course, if you draw that tiny little, I'm going to use this feature. Say that corresponding rectangle is somewhere here. And this side is the R, and this side is the theta now, isn't it? You see, they don't correspond. This area is not same as this thing now, but this is the R, the theta, so we are missing that R. So we need to find the relationship between the dy dx here and the R, the theta, and that happens to be R, we know. But how do we formalize this is our task here. Good. Okay, now, so let's generalize this. So say we have some kind of region D of f of, let's say, x and y, and then dy dx. And then we want to change that to same region, but we just want to go with any two variable, uv, any relationship in x, y, and uv will do, right? And then we have du and dv. And then my question is, what goes here? As you found out, that happens to be R in this case, if it's polar rectangular. And in last year, it happens to be just dx over du in this case, right? But we have two variables, and these, it's not like x is related to u and y is related. No, it's not. There's, for example, here, in this, even in this example, see, x is r cosine theta and y is r sine theta, isn't it? You see, they are both related, intertwined. So coming up with a general formula for that is not really that easy. You get it? Okay, so let's do it. Here's a general theory to develop. Say, here's a coordinate. Okay, and I'm gonna make a copy of that same coordinate and put them here. Okay, just like the same picture before. Let's call this thingy x and y. And this thing is now u and v, which is r and theta in previous example. Okay. Now, if I draw a little tiny rectangle here, maybe like that, does it look tilted to you? It is tilted, isn't it? Dang, huh? That's so weird. This thing has never tilted it for me. Let's just, oh, that's big. Say is this. Okay. So this thingy, this side is du and this side is dv, isn't it? What does that same shape look like in here? We don't know, right? But this previous pictures may be some kind of indicator that maybe it looks like that. And maybe it's a little curvy too. We just don't know, right? You can kind of see this shape turns into something like this. So this shape turns into something that looks like this. Good. And this is a rectangle. That's no longer a rectangle. But if it's infinitesimal size, then we can look at it as parallelogram. You get the idea? Okay, so in order to come up with the area of parallelogram, we just need a couple of things, right? Do you remember parallelogram area thingy? We need two vectors, right? So we need this vector right there. That's one vector we need. And we need another vector like that. Good. And then you can cross the vectors. So I'm going to call this vector A for now, and I'm going to call this vector B. And this dA right there is dA, isn't it? I need to find the area of that dA. You with me so far? Okay. So let's say here, say x is some kind of function, right? Of, let's say, g of u and v. Good. And then y is some kind of function, say h of u and v. This g and v, g and h kind of means these things. You know what I'm saying? Two variable, they are both two variable functions. In this case, r cosine theta, r sine theta. Okay. Now, how do we need to come up, how do we come up with that vector a and b is the main headache, isn't it? Okay, so let me introduce you to parametric surface. This is a little bit heavy, but I think you can handle it. Say we are used to vector function having t in here, right? Instead of t, two variable vector function uv. And I'm going to put that x thingy here, g of uv, I vector, and plus h of uv, j vector. How are we doing? This thingy is x of uv. You know what I'm saying? I'm just going to write x, and this thing is y. So it's the same as before. You know, instead of x and the t and yt, this thing is uv. This thingy and this thingy. It's still a vector function. Really? Does that give you some kind of area? Let's think about degree of freedom. When we had a t here, then it only has 1 degree of freedom, right? That's some kind of curve. Move back, forwards. Either you can move forward in that the line, well, curve, or move backward. But now we have 2 different degrees of freedom. Do you see it kind of gives you some kind of surface, if you will? Okay, now, so let's think about it. Vector A then can be given by this. Vector A, say, is it delta r in u direction? If I hold, let's say, if I move a little bit this way, then I move a little bit that way is the picture. You know what I'm saying? Let's go back to this thing. If I move r a little bit that way, then this thing moves a little bit that way, right? If I move theta a little bit up, then this thing moves that way. You know what I'm saying? So this is the r direction and this is the theta direction, isn't it? Right, that gives you that approximately parallelogram looking thingy. So if I just move slightly in u direction, then it's going to move in that direction. You know what I'm saying? Right. And then if I move slightly in v direction, then it maybe this thing moves in that direction. So do you understand that delta r in u direction? Okay, I'm going to write it. So this thing means, well then, r of u plus delta u, comma v as a constant, minus r of uv. Is that better? Okay, wait, that looks so familiar. Is it approximately equal to partial derivative with respect to r over partial derivative with respect to u, then du? Right, because if you divide this thing by du and take a limit, that's exactly what partial derivative was now, wasn't it? You want me to write down the partial derivative? You understand, you remember this definition, right? Okay, we only need to get over 1, because the other one is almost the same thing. So that vector b is your delta r in v direction now, isn't it? Namely, r, and then u as a constant, and we vary v, so v plus delta va minus r of uv. Good? You with me? And that's going to be approximately equal to partial derivative of r divided by partial derivative with respect to v times dv. Whew. We're done. Okay, so let me just, okay, then I'm gonna go back and say A, that's back to A. The A, I'm gonna zoom in a little bit. A was this partial R and then partial U, du. Let's compute what this thing is. Okay, we have a function here, right? We can compute it. So we'll take, this thing is x, so we'll take partial x over partial u, I vector, correct? Take a partial of this with respect to u. Remember that's x. And then the other one will take partial of y with respect to u, j vector, correct? And then times du is what a vector is. Du is necessary to make it infinitesimally small. Likewise, then the vector b will be partial r, partial v now, right? Because that's in v direction. dv, which will be, you take this thingy and take a derivative with respect to that variable v. So we have partial x over partial v, I vector, plus partial y over partial v, j vector, times dv. Most of the difficult thing is done. Are you with me? If anybody has a question, now is the time. Okay then, let's zoom out and get the perspective now. So dA, back to dA now. How would we calculate dA? Of course, like that, right? So only thing we have left is just physically do it. Okay, do you hear my gardener outside? Yeah, I really hate gardeners. They somehow know I'm having a recording, and they always do this. Okay. So that is ijk. We are crossing these two, right? So we'll have I, j, k, determinant, right, thingy. And then we have to take absolute value of that thingy, right? Like that. That's ugly. Okay, so we have partial x, partial u here, right? And then partial y and partial u. And this vector is 0 because we are only doing this in 2D, right? And then here, partial x over partial v, and here partial y over partial v, and this is 0. Are you with me? Okay, minor and cofactor thingy, right? So I is 0, j 0, so k is the only thing that survives, correct? So that is equal to magnitude of the determinant of partial x, partial u, partial y, partial u, partial x, partial v, partial y, and partial v, close k vector, take the magnitude of the vector A. Well, then k just drops out and it's just this thing, isn't it? Right? Yeah, I'm gonna do copy and paste. This is a lot of writing now. Let's paste it here. That is it. Okay. Now, there's a symbol, because this is a lot to write, right? So people abbreviate, this is weird looking thingy, so partial derivative of xy over partial derivative of uv. They write it like that. It does not mean anything. It's just a definition. Whatever that is means just, oh, I already copied it already, so it just means this thingy. Change the color. Does not want to change the color on me. Whatever. Erase that. Now it changes the color. I don't understand computers. Let's try one more attempt. Why wouldn't it change the color for? Now it's weird. One side is black, blue, and the other side is, oh yeah, it worked now. That thingy is the symbol for this, okay? It's just to take a determinant of that thing. And that there's a name for this. This is known as Jacobian. I guess somebody named Jacob came up with this. Shall we test it? Yes, we shall. So, let's go back and say, do you remember this? X was r cosine theta, and then y was r sine theta, right? Shall we convert this using our Jacobian idea now? Yeah, let's do that. So partial x, partial r is our u, and then theta is our v. You get it? And that gives you cosine theta, right? And then partial y over partial r, that gives you sine theta, correct? And then I always format it this way so that I can take a determinant without rewriting it. Partial x, partial theta is negative r sine theta. Good. And then partial y over partial theta is r cosine theta. Good. So what is the determinant of that thingy, or x Jacobian? Are you there yet? This minus this, isn't it? So we have r cosine squared theta minus negative r sine squared theta. Bang! Your r. Remember that r? So it's true. It works. Now we are going to do it in 3D. So suppose we have some kind of 3D coordinate system. I'm going to throw it, say, like that. And oh, not that. And then like that. And one more. Like that, right? So we have some kind of 3D coordinate system. Let's say this is u, v, and w, and I need a copy of this. So why don't I make a copy right now and paste it and put them right here. Okay, so this is u, and this is v, and this is a w coordinate, and transforming to x, y, and z. So this u, v, and z, I mean, sounds abstract, but you can think of this as a rho, v, theta in spherical coordinate. You know what I'm saying? Okay, so I'm gonna take some little tiny volume here, okay? Let's see if I can draw that thingy. So if I take tiny little volume like that, which looks like that. And if I transform it just like that rectangle becoming a parallelogram, this thing does not remain as, right, rectangle anymore. So maybe it becomes something that looks like parallelepiped that you guys looked. Maybe it becomes something like this. You know what I'm saying? Okay. So now let's get this. So if we vary the say u vector tiny bit, let's say this corner, wrong color. If you vary, I'm going to zoom in. So just a u vector a little bit, maybe it gives you. Why, how come this thing doesn't change the color? Okay, hold on. Okay. It gives you that thingy, that's the u in that direction, okay? Just to see, let you see all of that. And then, bad idea. I just don't want to put it because you cannot see it on that side. Okay, in the behind the line, that let's say there's a point, that's our point, and this is the u. You get it? And then this is dv, and this is dw. How's that? Okay, if you vary a tiny bit, then you create that. That's what dv is, right? du, dv, dw. Okay, how does that show up here then? Right? Okay, let's say this thingy, where's the corner? Let's say that corner is here. This is easiest. So here, and then let's say this little thingy vector is A due to the u movement. And this little thingy is vector B due to, let's say, v movement. And then this upward motion right here is vector C, which I'm going to put here, due to w movement. How about that? Good. You know that in spherical coordinate we had what is approximately the box that we just use the geometry to figure out the rho squared, sine phi, d rho, d phi, d theta thing. You know what I'm saying? So it's that thing. So far with me? Okay, then like before, we're going to compute what these ABC vectors are, okay? So let me go back and create this R vector that has U, V, and W in it, okay? And that thing is, of course, parametrized function with a function x, which is a function of U, V, W, I vector, and then function of y, and then U, V, W, J vector, and function of z, U, V, W, and comma, and then K vector. And then this looks scary and ugly, but think like this. Do you remember x in conversion from Cartesian to spherical coordinate? This x was like a rho sine phi cosine theta. You remember that thing? And this y was in spherical coordinate rho sine phi and sine theta. And then z was rho cosine phi and no theta in it. You remember this thing? So this is x, y, z as a function of u, v. So you can think of u as a rho, v as a phi, and w as a theta. But I'm trying to generalize it into any 3D coordinate transformation, not just spherical. You know what I'm saying? Okay, so this is a spherical example. Okay, now we have to find the A vector. So A vector up here, this one, this thing right here, right? So we just vary u a little bit, right? So we'll say that is delta r in u direction. Okay, and that is r of, and then you vary u a little bit like this. And then hold v and w constant minus r at original position u, v, and w. Do you agree with this thing? Picture-wise, this point minus that point, right? That minus this gives you delta r. Good. And that, if you do, don't write this, That's a derivative. That looks like derivative now, doesn't it? That's what partial derivative is. So instead of writing it like that, this is almost same thing as partial r partial u times du. How's that? Delta u. Delta u du are about the same thing in infinitesimal size. And some mathematicians hate that, but hey, if it was good enough for Lagrange, it is good enough for me. Okay, likewise, then vector b, let's say vector b was created by movement in v direction. Okay, so we do exactly the same thing in v direction. So that is r, and then u as a constant, and v. That v looks a little weird. Let me just write a regular v. V plus delta v and w minus r, and then v, v, and w. Three of the most look-alike letters in that grade. And then that is also partial derivative dv times dv here. You get it? Y'all with me? I know this is kind of abstract math, and you have to get used to it eventually. When you go to college, they all look like this. And that is varying now w slightly, so u, v stays, and then w plus delta w minus r of u, v, w. And that, of course, once again, is partial derivative with respect to w times dw. Whoosh. You with me? Okay. Then we'll just physically take partial derivatives. Okay. So let's take partial derivatives. So a vector, taking a partial, it was this, right? U, and then du. So a vector, r vector looked like this. So we are just taking a partial derivative of x, y, and z with respect to u now, isn't it? I'm going to leave it up there so you can see. So this is partial x partial u I vector plus partial y over partial u j vector and partial z over partial u k vector, correct? And then times du. You see, because r is made of x, y, and z, so you're just taking partial derivatives of all three of them. Good? With me? Okay. Likewise, then we just repeat the same thing for b. Let's see if I can recycle this. You know, whenever I try to do something clever like this, it usually backfires on me, but oh, looks like this time it's going to work. Yeah, I like it. And then all I have to do is change this to v. And that, and that to v. You with me? Of course, you have a heck of a time trying to catch up in writing, but hey, I give you the notes. Okay, then c vector, likewise, also is partial r, partial w times dw. I see I knew I missed something. This is v. Okay, and I'm going to recycle the work again. Paste. It goes all the way there, huh? Okay, hold on, I'm gonna erase this part and then bring it in there. So we do exactly the same thing, except this time this thing is w. You with me? Wow, do you see that 3 by 3 determinant coming up? Right, but that was a formula in pre-calc book, so let's derive that formula. Okay. So I'm going to blow up this picture that I have. Okay, and then draw it here. Let's see how good my artistic ability is. I need that. Wait, I want different color. Let's say it's black. Does not let me change the color, huh? For some reason. Let's change the color. Okay, it worked. And then I have to put another parallelogram. Let's say we have that. Oh, that worked. And then lastly, now I have to combine the two. So, okay, say this is parallelepiped. I mean, it's not great, but I think I can fudge it a little bit. Okay, that worked. Are you with me? Okay, and then we have these three vectors. Let's remember what we got. So I'm going to do that with red. So I'm going to throw these vectors in. This was my A. And this was my B. And this was my C. Good. Okay. So I have vector A here, and vector B here, and then vector C here. Okay. Let's do one thing first. Oh, let's say these two are easy, right? If I take the cross product of these two, what am I getting? Do you see I get this area, right? Do you see what I'm saying? So let's just get that area first, okay? So I'm gonna say B cross C. I'm gonna do B cross C first. And B cross C, of course, is I, J, K, and where's B and C? Oh, there's B and C's. I need a lot more space than that, so let's say I'm gonna write these guys first. Partial X, partial V, partial Y, partial V, and then partial Z and partial V, and underneath I have partial X, partial W, partial Y, partial W, and partial Z and partial W. And then on top I have I, J, and K. Oh, that's an ugly line. Okay, that's the determinant, the cross product. So far so good? And then of course I have to put dV and dW out here, not to forget. Okay, now, do I want to write it or not? I'm gonna write it. I think it's better to write it, okay? Because like every year I try to convince students without writing it and this thing backfires on me. So let's write it. Let's write the ugly determinant. So first I vector. Oh, this is a computer. What do you know? I can do this. Copy and paste. This is the I vector thingy, right? So far so good? Did I miscopy that? That's a K vector thingy. I'm gonna shove it at the end, and that's my K. Okay? I vector thingy is this thingy, right? So I'm gonna copy this one. Shrink it down. This is I vector thing, right? I realize I need a little more space than this, so I'm going to put in this thing here. With me? Are you with me? Or not? Give me some indicator so I know you have at least remote understanding of what's going on. And then J vector, that's headache, so let's just do it. J vector is this thingy and this thingy with a minus sign, right? So we have partial x over partial b, and then partial z over partial v, and then partial x over partial w, and then partial z over partial w. Why did I write this thing out here? Move it in a little bit. And then this is plus. J vector. Dang it. J vector. More space, more space. Why didn't I give you enough space in the beginning? Okay, this is plus here and then. Okay, this is what it is. So far, so good. Now, if we take the magnitude of this thingy, that's the area of this parallelogram, right? How do I find the volume of this thing, Superman's crystal, parallelepiped? We have to multiply this thing by some kind of height. Where is the height? Height is from there, somewhere inside this vector, isn't it? Let me flip this thing around so you can see it better. So we have this picture. Say we have a parallelogram, and this thing A, let's say vector A then sticks out like this. We have to press the right buttons. Say this is a vector A. And these guys are still here. Okay, so I flipped it over, so A appears to be longer, so let me make it longer so that it looks the same. Like this is what we have, isn't it? So in that orientation, this is B, and this is C, and this is A. Do you see that? And then rest of the parallelepiped is there, which I'm a little too afraid to draw. So far, so good. Now we have to compute H. H will look like this. This is H, isn't it? Right, perpendicular, you drop the perpendicular line to that plane, and that's your H, somewhere inside that crystal. How are we going to achieve that? Okay, let's try to remember. This is a B cross C cross product, isn't it? Cross product is a vector, it has a direction. Where does it has a magnitude of this area. So this thingy is magnitude of B cross C. But this is a vector. Which direction does that vector point towards? It's a perpendicular direction upward here, isn't it? This is the direction of B cross C, isn't it? Y'all see that? This is B cross C. Right? You with me? Now, so if I go parallel right there compared to this line, and this is perpendicular, do you see this is H right here? Okay, so far with me. And then let me call this angle, what's a nice Greek letter other than phi and theta? Somebody give me a nice Greek letter. We're running out of time, people.
Alpha.
Alpha. So predictable. I knew you were going to say alpha. Okay. Then what we have to do is this. So volume, area of the volume, TV, happens to be H times B cross C. So far with me? So far with me. But H happens to be A cosine alpha, isn't it? Good. B cross C is a scalar. I mean, this magnitude is scalar because we take the magnitude, but does that remind you of something? One scalar, another scalar, cosine alpha? Could that be A dot B cross C? Do you agree with this statement being same as that statement? Because AB cosine theta was A dot B. So this, in fact, is a dot product now, isn't it? So all I have to do is, because I have this vector, B cross C, laid out here, all I have to do is just dot that with A. You know what I'm saying? Okay, let's dot it. So this is a big project. Now let's go back and, oh, there's my A. So I can make a copy of this. Copy. This is my A. Hey, this teaching with the computer stuff is not really that bad, right? Here's my A. And then I'm gonna dot it with this is my B cross C that I have it computed nicely, right? I'm gonna make this A a little bit smaller. That A is kind of big. Okay, and then I'm gonna copy this monster. Paste it here. Resize it, of course, so it's reasonable and pretty. And put parentheses around. You know what I'm saying? You know what I'm saying? Okay, oh, I forgot one thing. One thing is du dv, right? Let's add that in. So we have this big parenthesis here, and this dv, dw, and A has that du up there, right? So finally, I'm gonna put it at the end. So this is du, the wrong color, that color, du, dv, dw. Wow, that's gigantic expression, but do you agree with that thing? So all we have to do is dot it, right? So this thingy times that, this thingy times that, this thingy times that, and we add it, right? You with me? Okay. Let's see how clever I can get with this computer stuff. Okay, I'm gonna have it out here. And then spread these guys apart a little bit. Okay, I think I'm done. So what we're going to have is, okay, instead of I'm dotting it with dx du, correct? Erase. My computer is frozen at the moment. Oh, it erased. So I need partial x and partial u here. Good. Say yes. Say something. And then partial y and partial u is here. And I need partial z and partial u is here. Do you agree with this statement? Do you not agree with this statement? If you are confused, now is a really good time to ask. And this we have du, dv, dw. Let's review what just happened. Okay, you were here with me up to the dot product. And then dot product meaning I multiply this I vector with the I vectors, that's this thingy, I color coordinated, and this J vector with this J vector component, and that's this thingy, minus sign, minus sign. This is plus, and this is minus. Good. And then this K vector component with this K vector component, and that's right here. Yeah. Well, is that really our triple scalar product? Let's compare that with scalar products. I'm going to recycle this thingy. And paste it here. Let's just say if I replace this thingy with partial x, partial u, partial y, partial u, and partial z, partial u. Do you see they are the same thing? Because if I wanted to take the determinant of this, I will use this first row as here, there, and there, and then regular minor and cofactor now, isn't it? Amazing, isn't it? So this kind of proves why that triple scalar product happens to be the volume of parallel pipette while we are at it. You get it? Okay, 5 minutes left. Application. We'll convert the Cartesian coordinate to spherical coordinate and see if we get our dv. What was our dv? Rho square sine phi, d rho d phi d theta, right? Yeah, let's do that. Okay.
Oh, Mr. Kim, I think you're missing the d, dv, dw.
Thank you so much. Thank you. I always forget that thing. du, dv, and dw, right? Yeah, that's essential. I always forget that thing. Okay, here we go. I'll go a little fast, and if we run out of time, you can quietly go. So x is equal to rho sine phi, right? Cosine theta. Y is equal to rho sine phi sine theta. And then z is equal to rho cosine phi. So far so good with me? Okay, I'm going to take, I regret writing it this way because I need a partial derivative and across. It's okay, I can do it. Okay, so I'm gonna take derivative with respect to rho. So partial x, partial rho, that's already partial. Partial rho is just sine phi cosine theta, and then partial y, partial rho. We have to organize these things. Sine phi, sine theta, and then partial z over partial rho is equal to cosine phi. You with me so far? Now I'm going to take partial with respect to phi. So partial x, partial phi. And the way I'm going to organize it is whatever goes in here, exactly in that order. You know what I'm saying? So I don't have to rewrite this thing inside the determinant. I would just imagine the whole thing. Okay, this is then rho cosine phi cosine theta. And then partial y, partial phi. That's ugly, really ugly partial. Partial phi is equal to rho cosine phi cosine theta. And then partial z over partial phi is equal to negative rho sine phi. With me? One more left. So partial x over partial theta is negative rho and sine phi sine theta. Partial y, partial theta is equal to rho sine phi and then cosine theta, and then partial z, partial theta. There's no theta in there, so it's 0. So far, so good. Let's take a determinant of this thing. Okay, determinant, you just imagine this gigantic determinant in here. You know what I'm saying? Okay, so let's do it. So the Jacobian of x, y, z over this thingy, and then our rho, phi, and theta is equal to which one should we take as a minor? We should totally take this rho, right? You know what I'm saying? Okay, so this thingy first. Should we take this column? Yeah, I think this column is a better idea. Let's take this column. So using this and then minor cofactor thingy, so we'll have cosine phi. Okay, and if we cross this out, we are having this thingy, right? So this minus this, so rho square sine phi cosine square, right? Okay, so we'll have rho square common factor, then watch this, sine phi cosine phi, and then cosine squared, and then this way, right, minus, make it plus rho square out here, so plus, so you have sine phi cosine phi sine square. With me? Do you see where this is going? Cosine square, sine square, that thing, you just, yeah, that's where it's going. The next one. So this one, this is minus negative 1, so it already gives you plus, and then rho, and then sine phi. With me? And then what we have is this thingy minus that thingy. Okay? So we have another rho in here as a common factor. And let's see, we are doing this. So this times this, so we have rho out here, sine square, cosine square. Good. Sine square phi cosine square theta. Good. Plus, and the other direction, sine square and minus sine makes that plus, and then sine square theta. You with me? Okay, lastly, and then we are doing this, which is 0 already, right? So let's see what we got. So we have cosine phi, a rho. I'm going to have rho squared first, and then cosine phi, and these two, sine squared, cosine squared. So it just gives me sine squared phi, cosine phi, which is this. Good. Very good. If I figure this, I get sine square, cosine square, and there's no square here. So sine phi. So far so good. And the second one, I will get rho squared, and then this thingy, sine square is a common factor, so I just get sine square, right? So I get sine cube phi. Good. And then common factor between the two, so rho square and sine phi is a common factor. And then what I have left is cosine square phi plus sine square phi. That is equal to 0, so we have that thing exactly the way we want it. Dang, huh? Okay. Number 14, rotated ellipse. We are evaluating this integral, this ugly quantity, but that much is not that bad, but it's the region that's killing us. This is the region R. U, right? So we definitely need coordinate transformation. Shall we do a little bit of review on rotated conics? Yeah, okay. So let's review rotated conics. Okay, first we have to figure out this degree of rotation, which we call theta, which appears to be 45 degrees at the moment. Did she use tangent or cotangent? I can go either way.
Tangent.
It was tangent. Okay, so we have tangent to theta is equal to, and then you have this b over a minus c, wasn't it? God, my memory is a little shady. It was just b, not 2b over b squared, right? Okay, and abc, or abc, right? Was it negative b? I don't remember. I think it was just b. We'll see. So we have negative 1 over a minus 1 minus 1. So this thingy becomes undefined, right? This is why people use cotangent, by the way, but we can still make this thing work because cotangent is easier. Where does tangent has a vertical asymptote at? Because undefined means vertical asymptote, correct? So tangent has vertical asymptote at pi over 2, correct? So that thing tells you that theta is equal to pi over 4. So our degree of rotation is pi over 4. With me? Okay, then what was our rotational matrix? Coordinate transformation rotational matrix. It was cosine theta, negative sine theta, cosine theta, right? X, this is x prime, y prime, I think. This was xy. No, yes. You want me to review that as well? How to rotate stuff in coordinate? Might as well, right? I can teach you why this is any degree of rotation of anything. You want to learn that? You don't want to learn that? Give me an indicator. We are on the recording. Either you want to learn it or you don't want to learn it. Okay, let's do this, right? We'll come back to this. This is a general coordinate transformation idea, okay? I'm going to delete this. I'm going to create a graph space. I think we can just do it without graph space. So we'll come back to this. Suppose we have, whoops. Okay. And then we have an I vector. And that I vector will, let's say, look like this. Okay. And then we want to rotate that I vector onto certain, so I'm gonna copy this. So after our transformation, we'll call it, what do you want to call it, M? Matrix M. Okay, because matrix is, oh, we don't know this, but when you multiply matrix by some vector, it transforms the vector. Okay, we'll only do rotation today, but so that same I vector, let's say, looks like this. I'm gonna make this thing longer too. This is more of a college stuff. It's called the linear algebra, by the way. So this is the rotation of theta degrees, okay? Somebody give me the coordinate of this vector. This has a length of 1 because it was I vector rotated. Oh, come on, children. How long is this side?
Sine theta.
Huh? So this is cosine theta. How long is this side?
Sine theta.
Theta. So this vector that you used to write is cosine theta sine theta, right? And this I vector, of course, I'm gonna still write it, is 1, 0, correct? Now, since we are using this, it's a little weird, but most mathematicians prefer this vector. What? That's a vector? No, why not? It's the same idea, right? 1, 0. Except we are going to do matrix multiplication, so this makes more sense. So this is known as row vector, this is known as column vector, okay? We can handle this. I know it's way like, next subject to this is called the linear algebra. So this thingy is same as then cosine theta and sine theta. Whatever that means. You with me so far? Okay, now, well, then let's do the same thing with the J vector. So J vector, last time we checked, let's see, that didn't work. Hold on, I'm gonna move it. That's J vector, correct? Which is, of course, 0, 1, which is also known as now 0, 1, like this, right? And then after theta degree rotation, then what does J vector become now? It's got to be perpendicular to that I vector, correct? So it's got to look like this. Say yes. Okay. We're going to figure out the coordinate of that thingy. This is theta right here, isn't it? So tell me what this component is. It's the same thing as that component right there. The length of this thing is still 1.
Sine theta.
Negative cosine theta you meant, right? Yeah, you totally meant it.
Wait, which part? Oh, sorry.
Negative cosine theta, this way. Okay, chance to redeem yourself. Tell me about this thing. Oh, whoa. Cosine theta? No, you totally meant negative sine theta, right? Opposite side.
That's what I said.
Oh my God. Yeah, of course you meant that because that's what you said. Okay, tell me what this side is.
Cosine theta.
That's ugly cosine. So this is cosine theta. Good. Oh, this is going to be great. Shall we write down what that coordinate is? Push it down a little bit. So this vector will have x negative sine theta and cosine theta, correct? Also known as negative sine theta, cosine theta column vector. Good. Here's a proposal. I propose our M coordinate transformation vector is whatever you want the I vector to be, this thingy, and sine theta here, and whatever you want the J vector after the transformation to be, I propose that is our rotational matrix. Really? Why? Shall we check? Let's check. So we'll check with M times I, right? Shall we? So what we have is cosine theta, sine theta, and this will explain why matrix multiplication is defined the way it is. Watch this. 1, 0, correct? Somebody multiply this matrix and tell me what you get. Oh, come on. This times this plus this times that. I mean, this times this plus this times that. So you have cosine theta here. Good. And then this times 1 and this times 0. So we have sine theta. Wait, isn't that exactly what this column is? Yeah. And that's exactly what we want it to be. So this was irrelevant when you're dealing with I vector now, wasn't it? It just picks out this column. Okay, let's do the same thing with J vector. Okay, so changing this to J. So we're changing this vector to 0, 1. And let's see what that thing gives us. This times this plus this times that, which is negative sine theta. That's ugly sign. And this one times 0, this one, oh. And that's exactly what we want it to be. So if you multiply this with the 0, 1 vector, it just picks out this column. You see why matrix multiplication is defined the way it did, and this thing does the job. And since all vectors in this big word coming vector space is just some I plus some J, isn't it? Some scalar times I plus some scalars times J. So if you hit it with this matrix, then you can rotate that vector exactly by theta degrees. Amazing, isn't it? Yeah, it was truly amazing. Okay, now back to our problem. So coordinate matrix was, I'm gonna push these things down. So see, previously, what does our UV look like? I should have made a copy of that coordinate before. But UV will be just regular, you know, and then if you rotate UV, then we get XY coordinate, right? So that's what we are getting at. So our matrix coordination transformation, our XY will be our rotational matrix. Now we know UV or X prime, Y prime last year, but we'll just use UV. You know what I'm saying? So this will look like this. After performing, so this vector UV, whatever that is, right? I'm using this thing, I'm calling these things vector now, they are vectors. So this is cosine theta U minus sine theta V, right? This times this, this times that. And then bottom here, sine theta U plus cosine theta V. This looks a little more familiar now, doesn't it? So at 45 degree, then let's see if we really get this thingy back, okay? So at 45 degree rotation, let's see what we got. What's cosine 45 degrees?
Oh, 1 over root 2.
1 over root 2, root over 2, 1 over root 2, right? 1 over root 2, and then U, good, plus 1 over root 2. Oh. Why are they giving us this weird thing? Ah, yeah, this is review. And then minus 1 over root 2 V. And this will be 1 over root 2 U plus 1 over root 2 V. Okay? And if we do all of that, then we can rotate this ellipse back. So that thingy was pushing it a little more. So what we have is this. You know what I'm saying? And this is UV. So far, so good. So if we hit this thingy with a regular ellipse, with that matrix, then it becomes this. So far with me? And then we're not going to get into how to convert this into this, because that's not what they want us to do. Why are they doing this then? Right? They want this thing to shrink. They want us to shrink this thing and actually make it a circle as well. So this is not just pure rotation, but rotation plus the scaling in both directions. Yikes. So those two are going on at the same time in this problem. You get it? Okay, but at least we know what that thing is, right? So all we have to do is just scale it to the some number in front. So if I put root 2 here, and then negative 2 over root 2 over 3, and then root 2 here and negative root 2 over 3, then that's exactly what our transformation is, which will rotate and stretch at the same time. Good? Can you somewhat imagine that much? Okay, I'm gonna copy this thingy and then go way down and restart the whole problem now. Okay, let's say here. Okay, and then we have this thingy. Okay. Okay, now let's do this. So how are we going to have this thingy worked out then, right? So we use this coordinate transformation instead of just cosine sine. You know what I'm saying? Okay. Now all we have to do is just plug it in here, right? Do you want to calculate the Jacobian first, or do you want to convert it into regular nice ellipse, which will turn out to be a circle? Still your choice.
Can you convert it first?
Convert it first. So I'm gonna do this. X squared minus xy plus y squared is equal to your x, which is this. So I will have root 2 u minus root 2/3 v squared plus u minus, and then this is horrible algebra, isn't it? Root 2 u minus root 2/3 v times, I'm gonna push this thing out because I don't have enough space. Stay there for now. And then times y, and y is the second one, root 2 u plus root 2/3 v, and then plus root, that's weird, root 2 u plus root 2/3 v squared. And we're going to multiply this out. No, tell me it ain't so. Yes, it is. Okay. So this thing squared, 2u squared, good. Plus 2 times this times this. What do we get? 2 times, do you see at least 2 over root 3 uv? You with me? And then this thing e plus 2/3 v squared. Still with me? For the sanity's sake, I'm gonna line up the like terms, otherwise this will get crazy. So this one, oh, this one is difference of squares, isn't it? With a minus sign. Oh, thank God. So we have negative 2u squared and plus 2/3 v squared. So far so good? Say yes. Okay, now we're going to multiply that thingy out. So we have 2u squared, and then 2 times this times that, right? So we have plus 2 times 2/3 times uv, which is going to cancel that thingy up here. Oh my God, hallelujah, this is so good, isn't it? And then that thing is squared, so we have plus 2/3 v squared. Add them up. Then we have 2u squared. These two cancel, and what is that thingy? 2/3 to the 2. Wow! 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 Right? Oh, and that whole thing is equal to 2 here, right? So we can say, let's not do that. So we can say x squared minus xy plus y squared is equal to 2 transforms to 2u squared plus 2v squared is equal to 2, meaning u squared plus v squared is equal to 1. So we get unit circle out of it. I'm gonna throw that for you. So this is our new region. You know what I'm saying? I'm gonna make that black. So not only, you see, in previous case, this becomes that, right? but they wanted to shrink this as well by the factors so that this is that thing. So this is from UV to XY. Crazy transformation now, isn't it? And then they thought, well, okay, now you will never figure this thing out in your own, right? At least not this year. So they gave you what these transformation made. They basically gave you a matrix, right? These two and these two. Okay. Now, shall we integrate? Yeah. Well, one more thing. We still have to figure out Jacobian now, right? Okay. So remember that thing. Maybe I just don't have enough space, so I'm gonna write it. If I can remember it. Okay, somebody tell me what that is. So now Jacobian x is equal to √2 u minus 2/3, wasn't it? B. And then y was √2 u plus √2/3 b, correct? Because I need partial derivatives. This is just √2. Say yes. And then this thing dies. Say yes. Oh my God, you guys forgot? Okay, partial y over partial u is equal to just √2. That's ugly partial derivative. Okay, partial x over partial v is equal to negative, right? And then partial y over partial v is equal to, say yes. Okay, shall we figure out the Jacobian then? So therefore, Jacobian, the thingy that goes inside the integral, is equal to the determinant of √2 negative √2/3 and then √2/3. This way, 2 over √3 minus, so we get 4 over √3. You with me? You with me? Okay then. Then our thingy, what was our problem originally? I think it was this thingy, and then we have x squared minus xy plus y squared dA, right? Did I copy the problem down correctly? This thingy now becomes uv. So what was it? My equation up here. It becomes this, right? You know what I'm saying? So 2u, 2v, still that thingy, because that we have to keep 2, or the region looks like this. So we have 2u squared plus 2v squared, and then now our Jacobian, not to forget, Jacobian, right, that thingy, and then du dv. How about that? And still over our, what do you want to call this thing, d? Let's call this thing d. Good. Say yes. Now it's downhill. Should we go polar? Of course we should. So 4 √3 outside, and this is 2 r squared, right? See, that thingy and this thingy it's not, we don't want to do another Jacobian here, right? This is a polar coordinate, not between from xy to uv. This is from, xy to r theta. This is uv to r theta. So we pick up another r here, right? I'm gonna write it separately. So r squared, and then r d theta. R will vary from 0 to 1, theta will vary from 0 to 2 pi. Are you still with me? Okay. So take out another 2, so 8 over root 3, 0 to 2 pi, and this thing becomes r to the 4th power a. So here, therefore 1/4 from 0 to 1a, and then the theta. And this cancels, so we have 2 over root 3, and then theta just gives you 2 pi. So we have 4 pi over root 3. Whew. Dang, huh? What a problem. You can kind of sense what your test will look like now. And this is a take-home test, so all of this is a fair game. Actually, this thing inspires me about a great test problem. A little bit of research project. Any questions? Any other homework question? Technically, I didn't mention it, but this Jacobian is an absolute value of this thing. Okay, we didn't need it. Okay, you have to take the determinant and take an absolute value because it does not work with a negative sign because it's a magnitude of a cross product.